Precipitate. Okay. Outside of science, precipitate gets used in precipitation. And precipitation is the stuff that falls down out of the sky. Snow, rain, sleet, hail. Those are all precipitation. Precipitate means to fall down. A precipitate to a chemist is that solid that you form in an aqueous solution. Yesterday, made that yellow stuff. It all settled down to the bottom. My lead 2 iodide was a precipitate. These are the ones we use the down arrow for. So they sink down to the bottom. So precipitate is just another name for solid. And we are going to have to predict, and we just need a few general rules for solubility. You don't have to memorize them, just have to be able to use them. Okay, so here's the rules we're going to have to apply. The first 4 rules are about things that are soluble, able to be solution. That's what soluble means. Able, solution. That means they do dissolve in water. Okay, since we're talking about ionic compounds, the generic term for any ionic compound is a salt. So salt just means ionic compound. If your ionic compound has an alkali metal or ammonium in it, it will dissolve in water. Okay. You can copy them down if you want. If you want to copy them, just look at the yellow piece of paper because it says exactly that. That's where I got it from. And the first one is the only one about positive ions. All the rest of them are about negative ions. Okay? If you have nitrate or chlorate in it, it's going to be soluble. NO3, and we can expect the same rules for nitrites and chlorides. Expect nitrites and chlorides to behave like nitrates and chlorates. Fact is, here in Rancho Cucamonga, we have a problem. They used to manufacture rocket fuel here. Ammonium perchlorate. It's the stuff that was the solid rocket boosters on the shuttle. Okay. Well, they did not have good hygiene at their plant, and the water came, and when it rains on ammonium perchlorate, perchlorates dissolve in water. So the rain would dissolve in the ammonium perchlorate and take that perchlorate down into the groundwater. Okay. So several of the wells that we used to get our water from around here are now contaminated with perchlorate. And you can't get it out because you can't make it a solid in a solution because it is always soluble. So you can't put something in to make it solid so you can filter it out because it will always stay dissolved. So we've got a real issue with how we're going to get that perchlorate out of the wells that we get our water from. Because it always dissolves, just like chlorates. Sulfates will dissolve unless they're on this list. Silver, lead, mercury 1, barium, strontium, silver, most chlorides will dissolve. Oh, okay, sulfites, you can expect to behave like sulfates. Chlorides are soluble. You would expect iodides, bromides to behave the same way. That's going to be your best guess because it's going to be in the same column. The exceptions mean that means that sulfates are soluble, but silver sulfate wouldn't be soluble. Chlorides are soluble, but lead 2 chloride wouldn't be soluble. Solid ionic compound. So it's a generic term for all. So we use salt for a specific salt. Actually, probably what they call table salt, which is the more common name. So, I mean, because here's a clue that they're all salts. You've got Epsom salts, right? So all of these are about lists of things that will dissolve, that won't be a solid. These are the things that will be a solid. Carbonates, phosphates, chromates, sulfides, hydroxides. But that sets up a condition where you have a conflict. And we said everything with an alkali metal would dissolve. Everything with a carbonate wouldn't dissolve. Will sodium carbonate dissolve? The sodium says yes, the carbonate says no. The answer is rule 1 wins. That's why it's rule 1. Make sense? Okay, sodium carbonate, rule 1 is the only one about positive ions. Okay? So if you've got a positive ion like sodium hooked to carbonate, the carbonate part says it won't dissolve. The sodium part says it will dissolve. The will dissolve part wins. If you have a conflict, the will dissolve part wins. So that's what that, unless they fall under rule number 1 means on here. So here is the same copy of what I just put on the screen. So let's look and see. Is LiBr soluble? Here's how I approach it. I look for rule 1 first, because if rule 1 applies, I'm done, and I don't have to look at anything else. If rule 1 doesn't apply, then I need to look at the negative piece. So I look at the positive piece and see if it's an alkali metal or ammonium. If it is, I'm done. If it's not, I got to look at the negative piece. Make sense? So, is lithium bromide soluble? Well, is lithium an alkali metal? Yep, I'm done. Because of number 1, alkali metals are soluble. BaNO3(2), is it soluble? Okay. First, is Ba an alkali metal? No, it's alkaline earth metal. So the answer to that is no. What's the negative piece? Negative piece is NO3, which is nitrate. Which rule says stuff about nitrate? Rule 2, and it says nitrates are soluble. So it's yes, we saw because of rule number 2. Calcium sulfate. Is it soluble? Check the positive piece, calcium. Is that an alkali metal? No. So now I need to look at the negative piece, sulfates. It says sulfates are soluble, but then it gives a list of exceptions. Is calcium on that list? No. So we're going to follow the rule then. It's not an exception, so it's yes because of rule number 3. PbCl2. Is it soluble? No. Is Pb an alkali metal? Cl is chloride. Rule 4 talks about chlorides. It says they're soluble. Is PB one of the exceptions to that rule? Yes. So the answer is no, because number 4, it's an exception. If PB4 is not as predictable, that's really what it comes down to. Sometimes it's not as predictable. And by the way, these are just predictions, they're not guarantees. Big, broad, general rules like this. And we don't say how soluble they are. Could be just like, remember the magnesium oxide? When you shook it up in the test tube, it didn't look like it dissolved, but it still conducted better. So a little bit of that magnesium oxide dissolved. You just couldn't see it. Right? CaCO3. Is Ca an alkali metal? Is CO3 is carbonate. What rule applied to carbonate? Rule number 5. And number 5 says insoluble. So this is no. This is not soluble. Limestone doesn't dissolve. What about K2CO3? Because rule 1 applies here. Potassium's an alkali metal. But rule 5 also applies here. All right, so see how we got that situation. Potassium says it should dissolve. Carbonate says it should. And the answer is rule 1 wins. We should have never looked at the carbonate. You get that? Say, well, why do we do all that? So if you want to figure out if there's a reaction, it has to make a gas, solid, or water. And the ones you're going to be able to predict are solid and water. Okay? The reason why you're going to be able to predict water is because one piece will be an acid with an H, the other piece will be a hydroxide with an OH, and when you do the switch, H and OH are going to come together to make water. H is going to be the first in one of them, OH is going to be the second in the other one. When they switch partners, the H is going to end up next to the OH, and you're going to make water. So HOH is water, and if you make a product of water, you know it happened because you took the ions out of solution. When you put it in, it fell apart into ions. When it made water, it took those ions out of solution. Solids. The solids we're going to have to get from the solubility rules. So how are you going to apply the solubility rules? Well, you can't look at the reactants. You've got to do the exchange and see what you make, and see if either one or both of those are insoluble. Look to see if any of your products are a solid. If they are, the reaction is going to happen. If they're not, and it's not water, it's not going to happen. So this is what we didn't get to yesterday on that homework from last night. It said, predict whether it would be a precipitate. This is how you would do it, whether the reaction would happen. So this is what we're asking you to do. Just do the same thing you did last night and then go one step further. Okay, Mg plus NaOH. Well, I can see it's double replacement. So the Mg and the Na are going to switch places. So Mg is going to end up next to OH, and Na is going to end up next to SO4. Na is 1 plus, SO4 is 2 minus, so it needs to be Na2SO4, Mg 2 plus, OH is 1 minus, MgOH 2. I don't have to balance this. I just have to see what it makes. Okay? Now all I have to ask is either magnesium hydroxide or sodium sulfate a solid? Well, one at a time. Is magnesium an alkali metal or ammonium? No. Okay, then I have to look at the next thing, hydroxide. What does it say about hydroxides? Well, hydroxides are under rule number 5, right? Rule number 5 says hydroxides are insoluble, so they're going to be the solid. I now know this reaction is going to happen. No matter what happens with the other one, I know this one's going to happen. Okay? Turns out the next one starts with sodium, so it's still going to be aqueous. But it happens because the magnesium and hydroxide get pulled out of solution. Because they make a solid and sink down to the bottom. Make sense? Okay. H2SO4 and KOH. It's double replacement because I have 2 compounds. Positive pieces switch. The H and the K switch places. So the H ends up next to OH, and the K ends up next to SO4. SO4 is 2 minus, K is 1 plus, so it's K2SO4. I don't have to balance it to decide if it's going to happen. First one, HOH. What does that tell me? This water, what does that tell me? It happens. Because when I threw the H2SO4 and the KOH in the water, they fell apart. So when I started off, I had H pluses and OH minuses floating around. But that H plus ran into that OH minus and made water. There's no more H plus and OH minus floating around anymore. It's no longer an acid or a base. Okay? So we know this reaction is going to happen because it made water. K3PO4 plus FeF3. Well, the K and the Fe are going to switch places. The K is going to end up next to F. And the Fe is going to end up next to PO4. K is 1 plus, F is 1 minus. So that's the right equation. Fe, over here, since fluorine was 1 minus, the iron had to be 3 plus there. So it's 3 plus here. PO4 is 3 minus, so that ends up with 0. Just to decide whether it's going to happen, we don't have to balance. We just have to write the right formula. Okay. Will KF form a solid? Key is K, right? K is an alkali metal. Rule 1 applies. It's going to be aqueous. Is FePO4 going to form a solid? Well, Fe is not an alkali metal, so I can look at PO4, phosphate. Phosphate showed up in rule number 5, which said it was insoluble. So this reaction happens because it makes iron 3 phosphate. That solid's going to sink to the bottom. Yesterday, when we put together PbNO3 2 and Ki, we made PbI2 and KNO3. One of those was yellow. Which one? Well, the key is it's sitting at the bottom of the test tube, right? So it's the one that was a solid. Which of those two would be a solid? Well, not the one with K or NO3. Right? Rule 1 and Rule 2 both say KNO3 will dissolve. You can dissolve a lot of KNO3. Okay? PB is not an alkali metal. I is not on my list, but iodine I'm going to expect to behave like chlorine. So my solid is the lead to iodine. If I have any doubts, I know it's not the KNO3, and I see the solid, so what's it got to be? If you know it's not KNO3, it's got to be PBI2, because you're actually looking at it. You don't have to decide whether this is going to make a solid. You just have to say which one it is. Okay. We said we lied to you, though. Because every aqueous compound, every aqueous ionic compound, is actually falling apart into ions. The solids, the liquids, and gases are whole compounds. PBI2 is sitting together at the bottom of the thing. But if it's aqueous and it's ionic, it's separate ions. This is a lie. There is no NaCl in your NaCl aqueous. It's all Na plus aqueous and Cl minus aqueous. So here's a balanced equation. But it's full of lies. Magnesium, an aqueous solution of magnesium chloride and an aqueous solution of potassium or lead 2 sulfate are mixed. They form an aqueous solution of magnesium sulfate and solid lead 2 chloride. But here's the lie. Is there really any MgCl2? Well, MgCl2 is an ionic compound. I throw it into water, it's going to fall apart into Mg2 plus and Cl minuses. There's not really any PbSO4. It's aqueous. It's really Pb2 plus and SO4 2 minus. On the product side, there's not really any MgSO4 because it's aqueous. It fell apart into ions. It would conduct electricity. The solution would conduct electricity because of it. The PbCl2 is together because it's a solid. It's sitting at the bottom of the container just like the PBI2 was. That's really what's in the dish. Before, they were all separate ions. The reason I had a reaction was some of those ions came together and separated themselves. That's what the solid, liquid, and gas is all about. It's about taking those ions out and separating them from the mixture. Because I haven't really changed the magnesium or the sulfate. They're still there. They were there when I started. They're there when I end, right? So, let's try this process for this equation. So we would have started off with me telling you, write the reaction for when Fe, Br3, and KOH react. And you would have done the double replacement and swapped it. I know it's not balanced. We don't have to balance it yet. We'll deal with balancing it in a little bit. So iron 3 bromide and potassium hydroxide make potassium bromide and iron 3 hydroxide. Is there really any iron 3 bromide? It says aqueous, that means it fell apart, right? So it's really Fe3 plus and Br minus. Is there really any KOH? Well, it says aqueous. So it's really the ions. K makes a 1 plus, OH makes a 1 minus, so it's K plus and OH minus. That's what my reactants really look like. Separate ions. Is there really any KBr? No, it's aqueous. It says aqueous when I'm done. It fell apart. Is there really any FeOH3? It stayed together, it's a solid. Extra hard? So this is what we got for our complete ionic equation, right? You notice something about this? What happened to the Br minus? Go ahead and say it, it's true. Nothing. Nothing happened to the Br minus. It was aqueous when I started. It's aqueous when I'm done. It's still just air in the liquid. Nothing has changed about the Br minus. What's changed about the K plus? Nothing. It was there at the beginning, it was there in the end. They didn't do anything. So the ions that don't do anything are named after the people who don't do anything. They're called spectator ions. They didn't change. And unlike spectators at a sporting event, these spectators, well, actually, you can do it at a sporting event too. You can still have the game, even if the spectators are eliminated. There was a soccer team in Italy whose fans were so rowdy, they said, you no longer get to have crowds at your games. The games will be on TV in an empty stadium. Still had the game without any spectators. So we just eliminate the spectators. If I eliminate the spectators, the K plus and the Br minus, what am I left with? I'm left with Fe3 plus and OH minus makes FeOH3. That's what really changes. So if I'm talking about what really changed, the iron grabbed onto the hydroxide and made a solid and sank to the bottom. That's really what changed. The K plus and the Br minus were there to make sure the iron and the hydroxide could dissolve. Right? So when you do that, it's no longer the complete ionic equation, now it's the net ionic equation. So that Fe3 plus OH minus was almost a net ionic equation. We eliminated the spectators. We should have balanced it. I mean, bizarre part is, here's something we haven't had to balance before because everything we've done so far is neutral. But now we need to balance it based on charge. Balance it based on charge, because if the charge is different on both sides, that means you created or destroyed electrons. And you don't have that power either. Not only can't you create or destroy atoms, you can't destroy the electrons either. So every electron has to be there. So that means the charges have to be the same total charge on both sides. One side's neutral, the other side's neutral. One side's 2 negative, the other side's got to be 2 negative. Make sense? So how do I balance this? 1 Fe, 1 Fe, 1 OH, 3 OHs. To balance it, I just need to put a 3 in front of OH. Okay. So that's how you write a net ionic equation for a double replacement reaction. You figure out what solid it's going to make. You get the ions that are going to make that solid. Right? You can also do net ionic equations for single replacement reactions. The first step is to turn it into complete and then eliminate spectators. That'll tell you what's net. By the way, the word net, it's a very important word. You'll get to know it when you start getting paychecks. Because if you go get a job at $10 an hour and work 40 hours a week, at the end of the week, they do not hand you a check for $400. Uncle Sam gets his chunk. The state of California gets their chunk. Somebody named FICA takes some of your money. And in the end, you get less than $400. What you take home is your net pay. It's what you really get. What really changes for you. So net means after all the incoming and outgoing. Okay, so is there really going to be any Al? Well, yeah. I can have aluminum by itself. Is there going to be any FeSO4? No, it says aqueous. So it's going to be Fe2 plus and SO4 2 minus. On the other side, is there going to be any Al2 SO4 3? No. There's going to be Al3 plus and SO4 2 minus. Is there going to be any Fe? It's not an ion, right? So it's going to be there. It's a piece of metal. So there's the complete ionic equation. What does the net ionic equation look like? Well, any spectators? Sulfates, right? Sulfates didn't change. So my net is Al plus Fe2 plus makes Al3 plus Fe. And then you balance it, and you would say, oh, this looks balanced already. But it's not. Say what, 1 Al, 1 Al, 1 Fe, 1 Fe, what's the problem? 2 plus on that side, 3 plus on this side. I can't destroy an electron. So they have to be the same charge on both sides. Where are 2 plus and 3 plus going to run into each other? It's 6 plus. So I'm going to have 3 Fe's and 2 Als, which means I would have 3 Fe's over here and 2 Als over there. Now, the Als are balanced, the Fe's are balanced, and the charge is balanced. It's 6 plus on both sides. If you went back up and balanced the top equation, you'd put a 2 in front of Al. You put a 3 in front of FeSO4 and a 3 in front of Fe. See how you've got your 2 Als, 2 Al3 pluses, your 3 Fe plus 2 pluses, and your 3 Fe's. Yeah. Because it was there when I started, and it was there when I ended, and it didn't change. So all it did was sit there and watch aluminum and iron change. It just, that's why they mean spectator. Okay, if it's there at the beginning and there at the end, it didn't change, that's a spectator. Okay. So what I need you to do with these, same kinds of reactions as yesterday. Don't try to do it in the space provided. Please, don't try to do it. Okay. You need to decide if there's going to be a reaction. Does it make a solid? What does the activity series say? Okay. If it does, I'm going to want to know why it happened. Lead 2 iodide is a solid. Or aluminum is higher on the activity, or lower on the activity, higher on the activity series than iron. Okay. Or it makes water. There's always going to be an answer. Solid, water, or activity. So it starts off with the same thing you did yesterday, you take it a couple steps further. Have a great